Well, good morning or good afternoon. This is the last of our notes on nuclear equations, and this is part 3. This will be on, we'll wrap up half-life and then talk about the 4 forces in the universe, 2 of which occur mostly in the nucleus of an atom. So last time in our notes, we talked about how strong the alpha, beta, and gamma particles are. We defined fission as the process of breaking a larger atom into a smaller. Fusion as, next page. Fusion, where is fusion? There we go. Fusion is taking small particles and building a bigger particle. Talked about splitting the atom, that a little bit of mass can be converted into a lot of energy when we multiply it by the Einstein's c, the constant, which turns out to be the speed of light. You get a lot of energy from a tiny bit of matter. We went over the notes on half-life, kind of talked about and did a couple little practice activities. So we're just going to continue on from here. We're still on part F of my notes from before. And there's an equation. Now I'm going to write the equation out that you can use. Now this is for the people that, hey, you like math equations. If you're not into math equations, you won't want to do this. I would like you all to write it out, but you're not required to use it. First off, give it a little bit of room. We're going to put, now this is every different textbook people or source of information will use different symbols. So NT, we're going to say this is for half-life. This is for mass remaining. Remain ING. Sorry about that. This is the mass. Let me rewrite that. Okay, there we go. So this NT stands for the mass remaining. This is after you've had half-life occurrences go by. So the amount of mass remaining can be done with an equation where you say you need to know the starting mass. Let me zoom in here so it's a little bit bigger. So the symbol for starting mass is going to be N sub 0, okay? So this stands for the starting mass. Maybe it's like 100 grams of material. Starting mass of your material. Then what you have to do, you have to multiply. Now this is N sub 0, okay? Like, you know, at 0 time is what we're talking about. Now let's put some parentheses here. We need to multiply that by a half. So it's the mass remaining so far is the starting mass, N sub 0, times a half. But it's not that easy. We've got to put it, there's a little exponent we're going to put up here, and that exponent isn't particularly easy. In fact, this exponent we're going to put up here itself is a fraction. So we're going to put the exponent is little t divided by, and I'm going to use little t with a half next to it. Now, so we've got a little t. So this is the exponent that we're multiplying this half to. The little t by itself here, that stands for how much time has elapsed. You know, they might say in a problem you had 100 grams of material and after 50 years, so that's the time elapsed. And then this one right here, this is your half-life time. This is how long the half-life is. So this is half-life time. In our last example, the half-life for carbon-14 was 5,730 years. Some elements in our practice problem, we said the half-life was 30 years. So you can solve for how much time has elapsed, or what the half-life time is, what the starting mass is, or what the mass remaining is, if you're comfortable using the math equations. And we're going to work these out. If you are comfortable with this, great. If you're not, you don't have to do it that way, and we'll work on those in a little bit. But now we're on to part G. Part G. So, oh, there's the bell. Actually, it's the beginning of lunch for me. So there we go. Part G in our notes here. And we're going to call this the 4 forces. The 4 forces in the universe. There are only 4 forces in the universe, according to science. We're familiar with the first 2. In fact, most of what we tend to think of as forces really are electromagnetic forces, but I'm getting ahead of myself. So, the first one, number 1, appropriately is we'll call big G. Okay, that's gravity. And in physics, you'll talk about that more, but gravity is just the attraction Objects are attracted to each other based upon their mass. They warp and bend space. I'm not going to get into that here, but so gravity is the first of the forces. Number 2, the second force. I'm going to abbreviate EM, electromagnetism. So let's write that out. Electro, and then magnetism. Took a scientist named Maxwell to figure out that electricity and magnetism, they're part of the same thing. People didn't realize that for a while until he did some studies and found out that electromagnetism, now this is most of the forces we're used to. This is friction, this is elastic forces. Most of the stuff we're used to is electromagnetic. Now, a big thing that's going to apply for us, one of the facets of electromagnetism is that like charges repel, like repels. For example, if you have a plus charge really close to a plus charge, they want to move away from each other. Or if you have negative charges next to each other, they want to move away from each other. Similar charges do not want to be close together. Now, opposites attract. Opposite charges attract. For example, a plus and a minus. Those two are attracted to each other. This is what pulls electrons towards the nucleus of an atom. So that's something we got to remember because that's going to come into play in a little bit. Now, these are the two forces that humanity first discovered. They were fairly easy for us to see. We deal with them every day. Now, the next one is these are about, maybe now a little over 100 years old, which for science is fairly new. So the third force is called the weak nuclear force. The weak, and then we're going to say nuclear because it happens in the nucleus of an atom. The weak nuclear force. And this is really just, this is a force that kind of allows a lot of nuclear reactions to occur. And for us, in our class, the biggest part of the weak nuclear force, this is the force that allows a neutron, which I'm going to do n sub 0. If you don't know that's a neutron, then I'll write it in there. This allows a neutron to change into a proton with a plus charge plus an electron, which we have written as E with a 0 mass and putting a -1 here. So as far as it applies for us, this is one of the forces that allows nuclear reactions to occur, and they call it the weak nuclear force. So there's the third of the forces in the universe. And the last force in the universe that affects us is going to be number 4. It's called the strong nuclear force. I know, you're like, that's it? The weak force and the strong force? Well, these were named by people who spoke English. If this had been discovered thousands of years ago, they probably would have called Magnus Forciae Nucleae or something weird like that. Strong nuclear force. So this is the fourth and the last of the 4 types of forces out there. Now, to understand this, okay, well, first I'm going to do it with a diagram, okay? So let's draw 2 protons fairly close to each other. So I'm going to draw down here a P with a plus, and I'm going to put a circle around it. That's a proton. And let's put, as is in the nucleus of an atom, you've got other protons in the nucleus. Now the problem is, according to electromagnetic forces here, like charges, like 2 protons with plus charges, they want to repel. And they do. They want to get away from each other. So we're going to draw, this is called a vector arrow. It's showing that you've got a force. This is a force vector arrow. We've got sides. I'm doing the side. I'm trying these. Okay, they were supposed to be the same size. Sorry about that. I got kind of goofed up there. So try to make them the best you can the same size. They want to be pushed apart from each other. But what scientists observed that protons jammed into the nucleus of an atom. Remember, Mr. Rutherford said that the nucleus of an atom is really small, then you got the electric shell out here. You've got all these positive charges shoved really close. They don't like that. But they stay together. So scientists said, hey, the electromagnetic forces want to push these apart, but in the nucleus of an atom, they don't. So how can we explain that? So what the scientists said, well, this is a really strong repulsion here. There must be a really strong force pushing against this to keep the protons in the nucleus. So now we're going to draw two arrows here. This arrow here, we're going to label the strong force, because this is a S-T-R-O-N-G. It must be a very strong force. I'll just leave force, pushing this way. And on this one, there must be a force, a very strong force, the same amount of force that is trying to pull these apart to neutralize this. So what happens is, this is the strong force pushing towards the center of the atom. You've got this force right here. We can label that is the electromagnetic forces trying to repel each other, EM forces. So what the strong nuclear force is, it's the force that overcomes the repulsion of like charges. So I'm going to write down a definition for that here on there. So let's see. The strong nuclear force, it allows protons, I'm going to abbreviate with a P plus, protons to be pulled very close, and let's make very, very big and bold if you can, very close. That's supposed to be close right there, in the nucleus. So we have, this allows the protons to be pulled very close in the nucleus, overcoming the plus charge repulsion. There we go. So there we go. We are done with our notes on nuclear chemistry.